Here we'll talk about Bayes' rule, which is a theorem or formula or helpful technique to determine conditional probabilities when the tree diagram itself does not directly give us that conditional probability. To illustrate it, or to motivate why we would need Bayes' rule, I have here a probability tree diagram based on data from Michael Radalay's research on sentencing case files in Florida in the mid 1970s. So these cases were for death sentence rulings where he examined the data in terms of whether the defendant was black or white, and then whether the victim was black or white in the specific case. So for the death sentence usage in Florida at this time, pretty much exclusively for violent crime. So this tree diagram represents, first of all, the proportion or the probability of the cases being whether or not the sentenced was black or white. So that's A or A bar. And for each of these possibilities, we examine whether the victim in the case was black or white. And that gives us our B or B bar. So from this tree diagram, we can determine some probabilities, like what's the probability that the victim in a case was white given the defendant is black, or what's the probability that a victim is black given the defendant is white. But what if we wanted to determine a conditional probability in the other direction? So, for example, what's the probability that a sentenced defendant is black given we know the victim is white? So that flips our probability tree diagram on its head. And if we're just given the probability tree diagram, it seems like there's no direct way to determine the answer to the question like that. Or of a question like, what's the probability of a sentenced defendant being white given we know the victim was black? For that, we use Bayes' rule, which I will write explicitly now. Bayes' rule can be written as the probability of A given B has occurred is the probability of A times the probability of B given A all over that same expression, the probability of A times the probability of B given A, plus the probability of A bar times the probability of B given A bar. So what we're doing here is, if you recognize this as a probability of intersections, we're looking at the probability of A intersect B out of the proportion of the probability of, again, A intersect B plus the probability of A bar intersect B. And the reason why we do this is because essentially what we're doing now is we're actually finding this probability by partitioning B in terms of A and A bar. So in other words, if we go back to this example, to find out the probability that a defendant is black given the victim was white, we find the probability of, so that is black given the victim is white is in this region. So we're looking at this branch. So this probability, right, is the numerator, and we take that out of that probability plus this probability. So the part that doesn't change is that we know that the victim is white, but the part that changes is whether or not it came from the black defendant branch or the white defendant branch. So if we want to explicitly calculate that, we should write it out. Probability of a black defendant given white victim is equal to the probability of a black defendant times the probability of white victim given black defendant all over that same expression plus the probability of a, in this case, what's changing now is we're swapping out A for A bar. So instead of a black defendant, we're going to look at white defendant times the probability of a white victim given a white defendant. And if we go ahead and calculate this, so we can fill in all the pieces here. So we need a few different probabilities here. So what's the probability of a black defendant and a white defendant? So probably a black defendant is 17 out of 36, and white defendant is 19 out of 36. So 17 out of 36, 17 out of 36, 19 out of 36. Okay, and now we need to find out the probability of a white victim given a black defendant or given a white defendant. So those probabilities are from the second branch, and we're looking at just the branches with white victims. So that's 11 out of 17 and 19 out of 19. So 11 out of 17 and 19 out of 19. So we fill that in now. So we have 17 over 36 times 11 over 17 divided by that same expression, 17 over 36 times 11 over 17, plus 19 over 36 times 19 over 19. And so what this will do now is there's going to be some nice cancellation here. So the 17s go away here, the 19s go away here. And we end up with 11 over 36 all over 11 out of 36 plus 19 out of 36. And all the denominators are the same, so it's actually going to work out really nicely. We'll end up with 11 out of 36 divided by, that would be 30 out of 36, which is 11 out of 30. That is our answer. So, in other words, what we found is that the probability that a case contains corresponds to a black defendant, given we know it came from a white victim, is roughly 0.3667, or just above 1/3 of the time.